Team, it's Mr. Z, and today we're going to be looking at some review before we do the final part of Lesson 2. Let's take a closer look. All right, so I want to look at this first situation. We're looking at y equals x squared, and then the inverse, which we discovered to be the radical of x, the square root of x. Notice in the top graph that it fails the horizontal line test. This is directly connected with the inverse. Since the original one failed the horizontal line test, the inverse will fail the vertical line test. What this means is that this top graph gives me information about the inverse. Let's look at our second example with the domain restriction. Because this top graph passes the horizontal line test, it means for sure that the inverse will pass the vertical line test. What the word invertible means is if it's invertible, the inverse will be a function. So when you test a horizontal line test, when you do this horizontal line test, you are also testing the inverse of another graph. Let's do one more though. So we're going to turn up the heat and we're going to graph the cubic and its inverse. So notice how we started with x squared. Now we're starting with x to the cube. And basically what I want you to notice is some key takeaways is that when I plugged in -2, I got -8. When I plugged in -1, I got -1. When I got 0, I got 0. I got 1 and 1, 2 and 8. So I'm going to graph these guys. -2, -8. Boom. -1, -1. 0, 0, 1, 1, 2, 8. This is what a cubic will look like. Now, technically, immediately, since I know that it is going to be odd, I know that it is invertible. I also know that because it passes the horizontal line test. But I can make that conclusion before I graph. Is it going to be a function? Yep. It passes the vertical line test. My domain, notice how it includes negatives, includes 0, includes positives. It goes left to right from negatives to positives, and it's going to increase. This means that my domain is going to be -infinity to +infinity. My range, going from bottom to top, is going to be the same because all numbers work. My x-intercept is going to be 0, 0. My y-intercept is 0, 0. So we're going to find the inverse of this guy. Remember the inverse, you want to replace all x's for y's and vice versa. Step 2, isolate y using inverses. And step 3, flip. So step 1, replace my x's with my y's. I'm going to now take the cube root, and I have to write the 3 to clarify that it's going to be the cube root instead of the square root. And I'm going to be left with just y. And I flip this, getting the cube root of x. So the inverse of this is the cube root of x. Now I've been stressing this, like in the beginning of the video. Since it is an invertible function, this means, without even looking at it, that this is going to be a yes. This graph is going to pass the vertical line test because it passes the horizontal line test. The inverse is connected to the original function. Now, the hard part is picking out the numbers that I'm going to use for my x's. I want nice outputs, which means I'm going to look at the list of perfect cubes. I'm going to look at 1 cubed, 2 cubed, 3 cubed, 4 cubed. This is going to be 1. This is going to be 8. This is going to be 27. And this is going to be 64. 64 is way too big. 27 is way too big to be on the graph. So I'm going to start with 8. And then this is going to produce 2. 2 times 2 times 2 is 8. My next one is going to be 1. And the cube root of that is going to be 1. When I plug in 0, well, it's going to be 0 as well. Now I'm going to go negative side. Negative 1 is going to be negative 1. The reason being is if I take 3 negative 1s, notice how that's negative 1. If I have negative 8, negative 2 times negative 2 times negative 2 will be negative 8. Selecting the inputs that are nice is going to depend on your knowledge and your ability to evaluate those radicals. After you get the points, this is just going to be a coordinate 8, 2, 1, 1, 0, 0, negative 1, negative 1, and negative 8, negative 2. So I get the graph in this guy. Voila. Notice it does indeed pass the vertical line test. For my domain, notice how all of my numbers are included, negative infinity to positive infinity. My range, all of negatives are included and my positives are included. They're going to constantly, slowly get lower and lower and lower and higher and higher and higher. My x-intercept is still at 0, 0, and my y-intercept is at 0, 0. Notice how the inverse is related to the original. Let's go back to the other previous example as well. Let's look at the first example. Pause and see if you can figure out what conclusions. Notice this main idea, and I'm going to write it over here on the side. The idea is if the original passes the horizontal line test, what this means is that it is going to be called invertible. Invertible means the inverse is a function which also means that the inverse will pass the vertical line test. I also know that this is the situation when x is to a odd power. Cough, cough, nod, nod, hint, hint. X to the third, x is to an odd power. It is invertible. Therefore, the second graph is going to be a function. It is a function because the second graph passes the vertical line test. This is connected to the first graph because the first graph passes the horizontal line test. The horizontal line test is connected to the inverse's vertical line test. Okay, let's do a couple more examples. So the inverses of power functions. Given each power function, write the inverse of each and include any restrictions so that the inverse is a function. So this is basically, this restriction part is going to come from when we're dealing with evens. When you're dealing with even powers, you're going to need to do a restriction. Oh, the first one is even. So I know that the inverse, when I switch it, it's going to be x is equal to y to the fourth. This is going to end up to be y is equal to the fourth root of x. And because it's originally even, I need to say that y, here, I need a little more room. So this guy, this is my original guy, my transformation. So x is equal to y to the fourth. That means x has to be greater than or equal to 0, which means for the inverse, y is going to be greater than or equal to 0. This next one, x to the 7th. Again, I'm going to flip my x's and my y's. X is equal to y to the 7th. It is odd, so I don't really have to worry about it. Odd. Because it's odd, I can simply write the inverse as y is equal to the 7th root of x. This next problem, well, it's to an odd power. So when I replace my x's with my y's, x is equal to y to the 5th. That is going to be y is equal to the 5th root of x. Here, this next one, this is odd as well. When I flip my x's and my y's to write my inverse, x is going to be y to the 57th. And when I solve it, it's going to be y to the 57th root of x. Here, this is even. So my first step is the same. I flip my x's and my y's. And here, I have to just remember my original has to be x is greater than or equal to 0. So when I solve my inverse, it's going to be y is greater than 0. Likewise, this next one is even. And I can even jump ahead saying that y is equal to the 314th root of x when y is greater than or equal to 0. This restriction is created because it's even. Specifically, I'm going to jump back. Part 2, we looked at the restriction. All this restriction does is it creates a situation where it's invertible, and that means that the inverse will be a function.